In today's video, we're going to continue our discussion of radioactivity by looking at how we can detect that radiation and how quickly the radiation occurs. Last time, to review, we went over the different types of particles that can be emitted, starting with alpha particles. An alpha particle is a lot like the helium atom. It contains 2 protons and 2 neutrons. So what we observe when a parent nuclide undergoes alpha decay, we're going to see a change in the mass. It's going to drop by 4, and we're going to lose 2 protons. Again, with any nuclear reaction, you want to make sure that you have conservation of the subatomic particles. And so the sum of the numbers, our atomic masses, should be, or our atomic numbers, should equal on both sides. So here we have 234 plus 4 gives us 238, and then our atomic number should also be conserved because we have the same number of protons. So here, that 90 plus 2 gives us 92, which is what we started with. Another type of particle that can be emitted is a beta particle, which is really just like an electron. And when a beta particle is emitted, we're going to see that we gain a proton as that neutron becomes a proton. Yet again, our mass number should stay the same. Those beta particles are massless. Beta particles can not only be emitted, but they can also be absorbed by the nucleus. So an electron, a low-lying and with a low-lying, low-energy electron can be absorbed by the nucleus, and when that happens, a proton becomes a neutron. So we lose a proton, yet again, the number of nucleons, which is protons and neutrons, remains the same. We also talked a little bit about gamma particles, and gamma particles are really just photons that contain energy. We didn't go over any specific reactions, but what you would see is again that because it's a photon, it doesn't contain any mass or charge, and so our atomic number and our mass number should remain the same. And finally, we had a positron, and a positron is like an electron except for it's positively charged. So in positron emission, we see that a proton gets converted to a neutron. We're going to lose one of our protons, so our atomic number goes down by 1, and again, the number of nucleons remains the same. So if we have polonium-214 and that undergoes alpha decay, what daughter nuclide will form? So in looking at polonium, I see that it has an atomic number of 84, telling me that it has 84 protons and 130 neutrons. If this undergoes alpha decay, what we'll observe is that one of the particles that is emitted contains 4 nucleons, and 2 of those nucleons being protons, which means that the other particle that is emitted has to contain 82 protons. 82 plus 2 gives me 84, and then it's going to contain a total of 210 nucleons, or protons plus neutrons. So now what I do is I need to look at the atomic number here to determine which symbol to use. And when I look to my periodic table, I see that lead represents the symbol of an atom that contains 82 protons. How can we detect these emitted radiated particles? Well, they all have energy, and so we can use changes, either chemical or physical changes, in order to measure the radiation. So one of the simplest ways to detect radiation is that you can have a photographic film that once it comes into contact with those emitted particles, it's going to fog. And so this is a quick way for employees working at facilities where there's stored radiation or radioactive materials to identify if they're in a place that's hazardous to their health. They just look at their badge. If their badge starts to fog up, they know that they're in an area where there's significant radiation. Or we can have a device that can detect the radiation. And the two devices I'm going to discuss is the Geiger counter, a Geiger-Moller counter. With the Geiger-Moller counter, there's argon atoms contained within this tube. The radiation will cause that argon to ionize, and then when the ionized argon comes into contact with this rod, it generates a small electric current that then results in a little beep in the Geiger counter. The other thing that we can use is a scintillation counter. A scintillation counter uses the radiation and the interaction of the radiation with a phosphorescent material to generate a photon, and then that photon can be detected. Irrespective of what type of nuclear reaction we're looking at, these nuclear reactions undergo first order kinetics. So we're going to see that they will have the same half-life regardless of how much material we start with. And we know that that half-life will be the same, again, no matter where we are in our curve. So down here, if we're looking at the decay of radon-220, for it to go to 1,000,000 atoms of the radon-220 down to 500,000 atoms, that takes about 1 minute. And so our half-life is going to be 1 minute. Half of 500,000 is going to be 250,000, shown here, and that's going to take 2 half-lives, or 2 minutes. So it doesn't matter where we are on the curve, we're going to see that to get to half the material we were at before, it's going to be the same amount of time. Different materials are going to have different half-lives, and depending upon the material, we'll see that this rate can be billions of years to billionths of a second. So there's a huge range in which these radioactive particles decay. However, if we know the half-life of the material, we would be able to calculate our rate constant and then use our integrated first order rate law in order to figure out how much is remaining or to figure out how much time has passed. So these radioactive decay processes are first order, and just as a reminder, the integrated rate law for a first order reaction is shown here. It's the natural log of the amount of substance you have at a given time, time t, divided by how much of that substance you start with initially, and that's going to be equal to negative our rate constant times the time. So N of t is the radioactive nuclei at time t, and then N naught is the initial number of our radioactive nuclei. So this represents the number left after t time has passed. This represents the number of radioactive particles initially. And since it's a first order process, we again see that it's independent of concentration, and so the half-life is going to be 0.693 divided by our rate constant, and that 0.693 is simply the natural log of 2. So now let's work through an example. We have iodine-131, which is radioactive and is used in thyroid treatments. It has a half-life of 8.05 days. If you're injected with 8.8 micrograms, how much is going to remain in your system after about a month? 32.2 days. There's two different ways that we can set up and solve this problem. The first being identify how many half-lives 32.2 days is. So to do this, we could say that we could take our total time, the 32.2 days, divided by the half-life, which represents the number of days per half-life, and that's going to tell us that we're at 4 half-lives. So then, initially I start with 8.8 micrograms. After 1 half-life, this will drop down to 4.4 micrograms. After 2 half-lives, I'll have 2.2 micrograms. 3 half-lives, 1.1 micrograms. And then my 4th half-life, I would see that I have 0.55 micrograms remaining. Or what we could do instead is we could use our integrated rate law and our half-life. So our first thing would be for us to determine what our rate constant is. So we know that our half-life is equal to 0.693 divided by our rate constant. Our half-life is 8.05 days, So we could plug that in here, rearrange and solve for K. And when we do that, we see that K is equal to 0.861 per day. Now I can take that and plug it into my integrated rate law. So I'm going to plug in my rate constant, 0.861 per day, in for K. My T is 32.2 days, and my initial concentration, or the amount of my initial radioactive material, is 8.8 micrograms. And now I simply need to multiply that 0.861 by 32.2, and that gives me 2.772. And then I'll take e to both sides to undo this natural log. So if we go up here, then that will cancel this natural log, and then I'll multiply 8.8 by e to the minus 2.772, and that gives me an N of T that's equal to 0.55 milligrams again, or micrograms. So regardless of how you set it up and solve it, you will get the same answer, whether you look at it in terms of the number of half-lives, or whether you look at it using the integrated rate law. However, in some cases, you're not going to be able to use the half-life. So in this example, we're given the half-life of 3.8 days, and we want to know how much of a 10.2 gram sample remains after 30 days. So now that 30 days divided by 3.8 doesn't give us a whole number of half-lives. So we're going to use that second setup to figure out how much of our sample remains. So first, again, we'll use the half-life to find our first order rate constant, and we'll use the half-life equation for this. We know that the half-life is 3.8 days. We can plug that in, rearrange, take 0.693 divided by that 3.8 to solve for K. So then what we get when we take 0.693 and divide it by the 3.8, we see that the half-life, that the rate constant is 0.182 inverse days. So now that we have our rate constant, we can use our first order integrated rate law. So we have K, we can plug that in. We know that N naught is our 10.2 grams. Again, here we have K. And we know that T is equal to 30 days. So plugging in, rearranging, and solving, we would first see that we have the natural log of our initial concentration. Ooh. So plugging in, we see that we had our initial amount, the 10.2 grams, and we would be able to find our N of T. So plugging that in, we have the natural log of NT divided by that 10.2 grams, which was our initial concentration, is equal to negative 0.182 times 30. That 0.182 times 30 is equal to 5.47. So then we take the natural log of both sides, or e to both sides to cancel out the natural log. E to the minus 5.47 is equal to 0.004206, which is equal to n of t over 10.2. Multiply both sides by 10.2, and we arrive at our answer that n of t is going to be equal to 0.0429 grams. And then it's always a good idea to make sure that this makes sense. So if it's 3.8 days and we've waited for the half-life and we've waited 30 days, we would expect that to undergo approximately 8 half-lives, 7.9 half-lives. So if we start at 10.2 and then we divide it by 8 times 2, which would be 16, we get 0.6375. And just to make sure that this makes sense, we can compare it to the number of half-lives, being 8. So 30 days is divided by 3.8 days per half-life gives us 7.9 half-lives, so call it 8. 8 half-lives is going to reduce our initial concentration to 1/256th, 2 to n, where n is your number of half-lives, of the original amount. So if we take that 10.2 divided by 256, we get 0.0398, which again, we've overestimated a little bit since we did it for 8 half-lives rather than the 7.9, and so we see that very closely matches what we would expect. So now let me have you guys try it on your own. In this iClicker question, we're looking at the alpha decay of uranium-235, which is one of the nuclides in spent nuclear fuel. And it decays, so it's one of the products that we were talking about, one of those waste products generated during nuclear reactions. And it takes 703 million years to decompose. How long will it take that uranium-235 to reach 10% of its initial amount? So notice that in this problem, you are still going to have to calculate your rate constant from your half-life. But then once you have that K value, you're actually going to use it to find T rather than use it to find your amount remaining. In this case, you're given the amount remaining. So if I have 10% of my initial amount, if you just say that you started with 100 grams, when you're down to 10%, that means that you're going to have 10 grams at that time. And so we have our NT, 10 grams. We have our N naught, 100 grams. We know our rate constant. You can plug it in and solve for it, and then you'll be able to rearrange and solve for T. When you do this, you should see that you get that T is equal to, so first we're going to use our half-life to calculate our rate constant. So we plug in our half-life, which is 703 million years, and when we divide 0.693 by that 703, we get 9.858 times 10 to the minus 4th million years. This gets plugged in here for K, and we would multiply that by T, and that's going to be equal to the natural log of our N of T, which we said was 10, divided by our N naught, which is 100. The natural log of 0.1 is equal to negative 0.2303. So I'm going to divide that by this negative 9.858 times 10 to the minus 4th. And that will be equal to T. So then T is going to be equal to 2.33 or 2,335 million years, which is 2.34 billion years. So that's a long time to be watching over that spent fuel. So notice we can go either way. We can figure out time given the half-life, or we can figure out how much material remains from the half-life by calculating our rate constant. And this is the basis of radiocarbon dating. So everything on Earth contains some amount of carbon, and that carbon can exist in different isotopes. One of those isotopes being C14. C14 can be generated through reaction with nitrogen 14, which will release a proton to give us that carbon 14. And it's a very, very small fraction of the total carbon that is composed of this C14, that is this C14 isotope. So that C14 isotope, it can be used to make carbon dioxide, and then that carbon dioxide is used by plants, consumed by plants and animals, plants during photosynthesis, and then animals will eat those plants, and then the carbon 14 will get integrated into their system and into their bones. So then we can look at how much carbon 14 is present, because that carbon 14 is unstable and will eventually emit a beta particle to go back to this nitrogen 14. And then we can use the half-life of the carbon 14, which is 5,730 years, to approximate the age of that material based on how much carbon we would expect to be in the atmosphere. And the amount of carbon 14 in the atmosphere is produced at about the same rate at which it decays, so that remains relatively constant. That equilibrium does. So we should see about the same amount of carbon 14 integrated into the system over time. It's just after it's integrated into the system, then how long has that system been sitting around to decompose to give us nitrogen 14? So let's look at an example of this, and I'm going to have you guys do it through an iClicker question. So just like we did before, we have the half-life, it's 5730. We can use that to calculate our rate constant. If our sample contains 3.6 dpm per gram of carbon, and that's carbon 14, in modern times we see 15 dpm per gram of carbon. So this here is going to be our N naught. And this here is how much carbon 14 remains in the sample after some time has passed. We can then calculate how old, in other words, we can calculate T for this animal skin. So again, to calculate our rate constant, we're going to have to take our 0.693 and divide it by the half-life, which the carbon 14 half-life is 5730 years. That's going to give us 1.209 times 10 to the minus fourth years, inverse years for our rate constant. And then the natural log of our NT, 3.6, divided by our N naught, 15, will be equal to negative 1.209, our K, times 10 to the minus fourth, times T. So the natural log of 3.6 over 15 is equal to negative 1.427. Then we would divide this by our rate constant, negative 1.209 times 10 to the minus fourth, and what we get is we get that T, gotta love it, we get that T is going to be equal to 11,804 years. So from this lecture and the last one, the objectives that we've discussed is that you can determine the type of decay or predict products given a decay if you know the type of decay. So the objectives we've discussed in both the last recording and this is determining the type of decay an isotope undergoes when you're given both the parent and daughter nucleides. You could also, if you were given the daughter nucleide and the parent nuclei, determine, you could also, given the daughter nucleide and the product, determine what your parent nucleide was, or vice versa. If you were told the type of decay and the parent nucleide, you would be able to determine the daughter nucleide. And then we went over kinetics of these nuclear reactions. So if you should be able to know what the half-life is and use that half-life to calculate a rate constant to then determine how much of your radioisotope remains after a given amount of time. Or if you were given the amount of the isotope that remains, you would be able to calculate how much time has passed.